Well, thank you for all getting back here efficiently and being ready to set up for the second half of day one of Big Data, second half of a big day of Big Data. Our first speaker for the afternoon is Ryan Adams from here at Harvard at the Paulson School of Engineering and Applied Sciences, and he runs the Harvard Intelligent Probabilistic Systems Laboratory, HIPS, I think it's called. Mm-hmm. He will be telling us about accelerating exact MCMC with subsets of data.
Thanks. Yeah, so I'm going to tell you about a couple of kind of two different projects today that are both kind of in the same sort of direction. And this direction is towards trying to handle large data sets, and here I mean sort of big N data sets using Bayesian methods and using approximate inference. In particular, using Markov chain Monte Carlo, which is one of the nice ways that we like to do inference in complicated Bayesian models. Now, we don't always want to be Bayesian, but sometimes we do. And we'd like to be able to do this even when we have really obnoxious posterior distributions. So the two things I'm going to tell you about are going to be both with the idea of trying to figure out how we can handle very large data sets where the actual computations that we do to perform inference step by step are actually only going to have to look at some subset of the data. Now, this is something that, for example, a lot of different optimization techniques for finding point estimates and so on are able to do because the kind of guarantees that we need for convergence of things like stochastic optimization methods tend to be a lot weaker, whereas Markov chain Monte Carlo is something that that's a little bit harder to work with and requires sort of stronger properties. The question is, can we kind of make a step towards getting the sort of same guarantees that we get from MCMC asymptotically while also only looking at sort of little bits of the data at any given moment, okay? And when I say exact MCMC here, what I mean is that we're going to be constructing Markov chains, so we're going to be constructing transition operators, that when we simulate those, that they are converging towards the true posterior distribution, not an approximation to it, but instead they're actually leaving the stationary, our target distribution is the stationary distribution, okay? So ideally, if we run these things long enough, then we get arbitrarily sort of good answers, okay? So that's the name of the game. The two methods I'm going to talk about are kind of complementary. One is something called Firefly Monte Carlo, which is a way to construct sort of a single exact Markov chain that at each step only looks at a randomized subset of the data, but nevertheless converges to the true full data posterior distribution. And then I'm also going to talk about a way to look at subsets of the data to parallelize single Markov chains, again, taking advantage of subsets of the data. And this first work is work with Dougal McLaurin, my student, and then the second work is primarily with Elaine Angelino, who's now with Mike at Berkeley, and some other folks as well doing systems research at Harvard, such as Margot Seltzer and Eddie Kohler. Okay, so before I sort of get started, I find it really helpful when we're gonna talk about big data. Big data, rather than being kind of like an abstract thing, I like to talk about some problems that I care about, and I feel like the best methodological research arises from, really thinking about sort of actual problems and inform that. There's a few different things that I care about that, like I said, kind of inform this. So one thing, for example, is thinking about how to deal with astronomical data, in particular, how to make inferences about all of the light sources that we can see in the visible universe and trying to infer what their redshifts are so that we can understand the sort of early structure of the universe and hopefully find things like dark energy. This is something that has a lot, even though it's a very large data set, it still benefits from being Bayesian because there's a lot of uncertainty associated with these very weak signals. But we're nevertheless trying to deal with survey data, so we've got billions and billions of images, and of course there are billions and billions of objects that we care about, galaxies and stars and quasars and so on. I also collaborate with folks in neuroscience, so this is the Harvard Medical School, in particular Bob Data, where what we're trying to do is use computer vision techniques and unsupervised learning and ideas from Bayesian nonparametrics to try to infer quantitative structure, to make quantitative statements about mouse behavior, to go from the very large sort of inter-observer error rates that we often see with grad students labeling frames of video, to instead have something that's not anthropocentric and that doesn't require sort of humans to make judgments and use human words to describe what mice are doing when we're trying to understand neural correlates and genetic correlates and different kinds of things that a mouse might get up to. The point here being that there's tons and tons of video, and we want to be able to process all of this stuff in a very flexible but rigorous way, and so we need good approximate inference techniques that can scale up. Then I also work with some folks here in the chemistry department at Harvard where we're trying to use machine learning for automated materials design. So in particular, this is work with Alana Spuru-Guzik. And we're trying to come up with new materials for organic photovoltaics. So you can think of this as being like trying to design plastic solar cells that are sort of much easier to construct and can biodegrade and so on and sort of be very environmentally friendly, but still be competitive with their silicon counterparts, as well as organic photovoltaics. So the idea being to have very nice flexible displays and kind of easier to construct displays than the ones that are in all of our laptops and phones right now. The idea here is to use machine learning techniques at scale to be able to use data from like density functional theory and simulations to predict the properties of completely new molecules and then make great choices about what things we're going to simulate and what things we're actually going to make in the laboratory. Okay, so this is just a little sort of smattering of some of the problems that have this kind of big data feel and that motivate me to think about large-scale statistical inference. Okay, going back to kind of being abstract, the setup that I'm going to talk about today for this is going to be a very, very simple kind of Bayesian modeling setup in which we have a collection of data and we have some set of parameters that we care about, and there's a likelihood that maps this the constructed distribution over the data given a set of parameters, and we have some prior over that parameters. And we can write down this posterior distribution that we care about, and the big thing here is that n is going to be large, and so this posterior distribution is going to be a product of potentially millions of factors. And it might be very expensive to compute. And the question is, how can we do the kinds of things we'd like to be able to do, integrating out latent variables, making predictions, making decisions, and so on, while sort of limiting how many times we have to look at these sort of millions of factors as we evaluate a particular hypothesis for theta. Okay? So this is kind of the name of the game. It's very cartoonish, but it kind of summarizes a lot of the problems we care about. In general, when we want to interrogate a posterior distribution and want to make queries of this form, we want to make predictions and so on, then we can almost always frame these as expectations. So the expectations under a posterior distribution. And so one of the ways that we like to actually do computation in practice is to estimate expectations under this target posterior distribution pi using Monte Carlo estimates, right? So this is taking a sample average. So if we get samples from pi, then we can evaluate whatever function, the function whose expectation we care about. We can just average the values of the function under pi. And then this has kind of properties that we understand. In general, it can be hard to sample from pi, right, directly. So in practice, what we often do is define some simpler kind of random walk. We define a Markov chain that we can simulate from, but that leaves pi invariant and satisfies some ergodicity properties. And the idea is that if we can simulate this easier thing, we can kind of run that forward and it will converge to pi. And so then we can compute sample averages under that Markov chain, and they'll still allow us to sort of ask the questions from the posterior that we'd like to be able to ask. So this is the stationarity condition for some transition operator t that we care about. Typically, we do something actually we ask for a sort of a stronger condition, but that one that's often easier to prove, which is that we want reversible chains that satisfy detailed balance, and so that looks like this. And the basic idea is we write down this Markov chain, we construct it in such a way that it leaves our target posterior distribution invariant, and then we use pseudo-random numbers from our computer to simulate this thing forward, and it will converge to pi, hopefully under relatively mild conditions, although it may take a long time. So the kind of sledgehammer of this kind of work is something called Metropolis-Hastings. The Metropolis-Hastings algorithm is a very nice idea. It basically just simulates from some easy random walk and then occasionally rejects one of the moves from that random walk. And if you carefully select when you reject the moves that it proposes, then instead of converging to this kind of other random walks marginal distribution, you would converge instead to pi. And the idea is that this kind of rejection procedure is based on a ratio of kind of where you are and where you're proposing to go. But there's other ideas as well, kind of recipes for cooking up transition operators that leave pi invariant. I really like the idea of slice sampling, for example. Slice sampling basically turns a problem of sampling from a non-uniform distribution into one from sampling from a really complicated uniform distribution, which is kind of really weird boundaries. It has some nice properties. In particular, it has the property that it tends to require less tuning than Metropolis Hastings. So if you want to build algorithms that lots of people can use, then it's kind of appealing to be able to hand them something that they can use without having to think too hard. So this is the kind of the name of the game here. The challenge for doing Markov chain Monte Carlo at scale, however, is that in general, of course, you only get information about your data and about the sort of things you want to estimate via this posterior density. Okay, and so you're going to have to evaluate the density every time you take a step in your Markov chain. And whether you're doing Metropolis Hastings or slice sampling or other things like Gibbs sampling and so on, it's really hard to get away from actually looking at the target. I mean, that's the only way you get information, right, is evaluating this thing point-wise. And as I said, the challenge is that we're going to need to take steps, to find a random walk that leaves this guy invariant, but every single time we take a step, we're going to have to evaluate, maybe a couple of million likelihoods. So for example, when I talk about these organic photovoltaics from the Harvard Clean Energy Project, then it's like 1.8 million factors, and now I think it's like close to 3 million different molecules in this data set. And every single time you take a step with your Markov chain, if you want to leave that true distribution invariant, you're going to have to look at that big target, and that can be very expensive. So the question is, how can we do this without having to look at all 2 million factors in this product and yet still get the sort of nice guarantees that we'd like to have as if we were looking at all the data every single time? So not surprisingly, this is something that I am not the first person to sort of say out loud. In fact, this is something that a lot of people are interested in, and it's been studied by, and this is just a smattering of papers over the last several years, of people trying to figure out how to do MCMC on large data sets where we can understand what happens when when you don't actually see everything at once. And most of these are kind of like nice heuristics that make a lot of sense, but in general, we don't have a strong theoretical understanding. Only a couple of these have properties that that have guarantees of the form. When you run the Markov chain forward, you'll converge to something that's not too far from the true distribution. And so at best, we have some kind of weak guarantees under relatively strong mixing conditions. But what we really want is to know that we're going to get the exactly right answer, okay? And we're not getting that in general from most of the methods proposed. What I'm going to tell you about first is an idea called Firefly Monte Carlo that, under some specific conditions, does allow you to sample exactly from the distribution we care about. I should say, when I say sample exactly, what I mean is it does leave the exact sort of full data, true posterior distribution invariant when we simulate it. And this, as I said, is work with my student Dougal McLaurin, who might be here somewhere. Okay. So Firefly it basically uses one of my favorite tricks from MCMC, and that's the idea of introducing auxiliary variables. Okay, so this seems kind of like a silly trick, but it comes up a lot, and it's very, very powerful for designing new kinds of algorithms. The idea is that there's some theta we care about, and some pi, some target distribution. And what we can do is add new variables to this Markov chain by writing down a larger joint distribution. So we introduce some size, and we have a theta and psi, and we create that joint distribution just by adding a conditional onto this. And this seems okay, because in general, if we now simulate from theta and psi together, then when we throw away the size, we leave our original marginal intact. That is to say that marginalizing away this little extra psi just doesn't change our answer at all. Okay, and so in general, that's not surprising and looks pretty trivial, but it has this sort of nice property that if you're clever about this conditional distribution, that is psi given theta, then when you condition on the current state of the Markov chain, the current state of size to update theta, sometimes interesting things happen. And the kinds of interesting things that might happen are things like faster mixing. So an algorithm like Svensson-Wang gives you faster mixing on icing models and related ideas by introducing auxiliary variables. Or things like Hamiltonian Monte Carlo potentially lets you use auxiliary variables to take advantage of sort of gradient information whenever you're sampling. It might make it easier to implement the algorithm. So slice sampling is an example of that, where you have this auxiliary slice height that turns it into a complicated but uniform distribution. And then there's also kind of really cool ideas like pseudo-marginal Markov chain Monte Carlo that allow you to add in kind of extra variables that are estimators of some unknown quantity and so on. So we're going to take advantage of this kind of trick, but do something a little bit different. What Firefly does is it's going to introduce a binary, so a Bernoulli variable, for every single one of the data. So we have 1 million data in our data set, 1 million molecules or something, that we're going to introduce into the Markov chain a new binary variable, one for every one of those data. All right, and I'm going to use a little shorthand here. I'm going to say for the nth likelihood, so this is a likelihood term, one of those factors for the nth datum. And this, from our point of view, is a function of theta. All right, I'm going to write L for that. And so that means that our posterior has this big product form still with L's now. And what we're going to do is we're going to go out and find a lower bound for this function L. All right, and so this is another function that just gives us that's hopefully simpler, that gives us a lower bound, and we're going to write that B. So again, we have now, if we had 1 million data, we now have 1 million lower bounds. Okay, and what we're going to do is use that lower bound to construct the conditional distribution for these auxiliary binary variables. Okay, and in particular, what we're going to say is that the probability that when you flip this nth coin, that it comes up as 1 is going to be proportional to, the probability that comes up as 0 is going to be proportional to the tightness of the bound. Okay, so this is just a Bernoulli distribution. And this, so if the bound is very tight at theta, then B will be very close to L, and this will be very close to 1, and the coin will be very likely to be 0. And then if the bound is very loose, then it's more likely to be 1. Okay, so we're going to flip a coin based on the tightness of these bounds at theta, and we're going to make them all conditionally independent given the thetas. Okay, so we're introducing a whole bunch of coin flips, one for every datum, and they're going to be based on the tightness of the nth bound. All right? And that seems like kind of like maybe kind of a weird thing to do. We're going to write out, but what's going to happen, we're going to write out now this joint distribution over not just the thetas that we care about, but also all of these binary variables z's, all these z sub n's. Okay, and the reason that's interesting is that when we condition on the z's, we'll get different forms for theta. In particular, if the zn is 0, then the likelihood terms cancel out, and we wind up with just the bound. Okay, so for every zn that is 0, when you're going to update the theta, going to update the parameters, you don't have to look at anything for which the zn is 0. So you're excluded, so some data now you do not have to examine. So if you have a very large number of zeros, then you don't have to look at those data. You could have 1 million data, and if sort of 900,000 of those are, have their auxiliary variables being 0, then you can make a step just based on 100,000 data instead. Okay, and then, so it's really simple. It's just basically observing that when this thing is 0, then this term appears and these two guys cancel out. And then this term is just 1. Okay, so it's a very simple trick with this conditional distribution. It happens to be the case that this thing goes away. And that means you can think about this, this means if you have tight bounds, so if your bounds tend to be tight, those values will tend to be 0, and the data for which your bounds are tight will tend to not need to be included in the posterior distribution. And instead, you'll include this term. Okay? Does that make sense? So you include the bound instead of the data. All right? And this has the property that as we marginalize away those z's, the marginal that we care about is left intact. So if you run the Markov chain forward in both theta and z, then the sort of trajectory of theta will be as though you were looking at all of the data every single time. Okay, so we're choosing a random subset of the data in such a way that marginalizing out that choice gives you the full data posterior distribution. Now, you might reasonably complain, okay, so that's great. You've replaced these, you've thrown away all of these likelihoods, but now you have 1 million bounds. But we have some flexibility in choosing our bound, right? And in particular, if we choose the bound such that it's something like a scaled exponential family, then it has the very nice property that this product of 1 million bounds just becomes one bound in the same class. So by this, I just mean the observation that if my bounds have the form e to the linear thing in some function of my parameters, then I can collect that very big product into just one thing just by summing those parameters. Okay, and in particular, as I add and remove the z's, then this allows me to just update by sort of updating those kind of sufficient statistics as I iterate. Okay, so I just need to add in parameters for the bounds when I'm including them, when I'm excluding the data, and then I can sort of pop them back out whenever I need to include those data again. And so this is what gives rise to the name Firefly Monte Carlo that Dougal came up with and that I really like, which is that the data are kind of going bright and dark as we iterate, right? So we can imagine this. So there's this very nice video that Dougal put together, which kind of illustrates this well. So here is this is basically kind of looking at a Markov chain where the data are being included and excluded on the right, and on the left is kind of the same problem but with the full data posterior. Okay, so the yellow dots along the bottom are different data that are being included. So sorry, every pixel in this bottom part is a piece of data, and it is being included in the computation of the posterior for every step if it's yellow, and it's not if it's black. And on the left is what we would do if we were just running MCMC forward in the usual kind of way, looking at every single datum at every single step. And on the right is what Firefly would do, randomly choosing some of the data to include as part of the Markov chain. Okay, and you'll notice that in this case the bounds are tight, and so this results in a very, very sparse set of data that needs to be included. And you can also see this is a particularly this kind of emphasizes why it's called Firefly Monte Carlo. Just the idea is that these guys are blinking sort of on and off, and some of them you'll notice stay on quite a long time. And this is basically because these are places where the typical theta that you get from the posterior distribution causes the bounds for that datum to be loose, and so then you need to include those data in almost every single step. Whereas if your bounds are tight at the typical theta, then you almost never need to include those data. The mixing can look horrible, but remember it's not that, so I should say that we don't have any theory on how much this damages the mixing in general. How much it damages it will be a function kind of the tightness of the bound, right? So if the bound is very tight for all of the typical thetas, then it doesn't damage mixing in any interesting way at all, right? Because it's basically just replacing one function with an approximation and then doing a very occasional correction to ensure that you're still getting the right answer. So it doesn't necessarily damage mixing, but that's more of an empirical and sort of heuristic argument than a sort of theoretical one. I mean, more generally, the main theoretical result here is that this is leaving the true full data distribution intact at all versus a more approximate kind of thing. Okay, so here's an example of kind of what this looks like. So we can imagine doing this with logistic regression with a very large set of data, and there's a very nice bound due to Tommy Yakla and Mike Jordan. And so we have our logistic likelihood, and then the idea is that this bound is a Gaussian distribution that you can make tight at any place you get to pick. So for example, one place you could imagine making it tight at the mode of the posterior, or at the map point, at the mode of the the mode of the prior, or at the map point at the mode of the posterior distribution, which is something that you can get without having to worry so much about guarantees about your convergence of your Markov chain. And so then the idea is that you are decomposing, in a sense, this likelihood into two pieces. One is the bound, and the other is the kind of residual, and mixing over these two in order to get the right answer. Okay, so we're mixing in theta, but then also bouncing back and forth between the bound and this kind of residual term. In general, of course, if you do the very naive thing of updating the z's, we have to update the z's as part of this to get the right answer. It presents some amount of challenge because if you do the really simple Gibbs type updates, then you're not really going to save anything because you're still going to have to touch all of the likelihoods in order to update the corresponding z's. But it turns out that you can come up with an interesting Metropolis-Hastings update that observes that you only have to look at the likelihoods if you're proposing to change the state of the z's, and so you can, and that combined with kind of nice data structures can allow you to not have to look at the likelihoods when you're updating the z's most of the time. So here's a kind of a toy example of what's going on. So the idea is that we have some theta parameters that we care about. Here, these are determining kind of the decision boundary for a simple logistic regression problem. And then we're introducing a binary variable for every single one of the data. And the idea is that we're updating the decision boundary conditioned on some of the data being light and dark, and then updating which of the data are light and dark, conditioned on those parameters. And it has a nice property that when we're making this kind of step of updating the decision boundary, then we only have to look at the subset that is currently bright. So we looked at a couple different kinds of problems to examine how this works. It has the very nice property, unlike some of the other kind of related methods, that once you introduce these auxiliary variables, you're allowed to use whatever operator you want on the thetas. Okay, so it doesn't have to be Metropolis Hastings if you like Langevin dynamics or Hamiltonian Monte Carlo, or you like to do slice sampling or something more complicated. It's totally fair game to use whatever operator you want on the thetas given the z's, and then you do these kind of MH updates on the z's. So this is a little set of problems to kind of look at mixing and look at the effect of tuning the tightness of the bound. So this is a couple of little image classification problems, as well as looking at these organic photovoltaics that we talked to the chemists about. And in the top case, we're doing a simple MH type update. In this second case here of a 3-class classification, we're using Langevin dynamics. And in the last case, using slice sampling with a couple different models. And the point here is that we're comparing the vanilla MCMC that you would do to what would happen if you essentially just chose the bound based on the bound to be tight essentially based on prior information. And then not surprisingly, it's kind of a middling win because the bound in general isn't tight enough to cause you to exclude a lot of data. But if you do something a little bit cleverer and you select the bound to be tight at the map location, so at the mode of the posterior distribution, then what happens is you can see in practice sort of up to like an order of magnitude speed up. So we're looking at many, many fewer likelihoods at every iteration, because most of the time we're replacing these data likelihoods instead with their bounds, okay? And then collapsing many of those bounds into just one. So this is kind of another view on this to kind of show how it works. In particular, essentially we're showing iterations of the Markov chain along the x-axis, and then the sort of number of likelihood evaluations per step as it goes. What's happening is that you'll see it kind of rise and then fall, and this because the bound is tight at the map, and so after it burns in, then that's the situation in which the bound is tight, and so it tends to not need very many data. In this case, the slice sampling, if you know about slice sampling, it does a kind of an adaptive search to determine where to take the next step. So although these have kind of fixed number of likelihoods per step, slice sampling jumps around in an interesting way, just so in case you're wondering why that one is jaggedy. And again, you can kind of see how it's using many, many fewer data after it burns in at kind of every single, at every step. So quick questions about Firefly. If not, I'll move on to talking about a way to parallelize using a different kind of idea of subsets of data. Yeah?
Is there a way to automate choosing the bounds to make it more automated for broader classes?
Good question. I mean, in general, choosing bounds for arbitrary problems is something that's kind of has an art to it. I mean, if you know a class of bounds and you're trying to decide, how to, make those tight, then you could, so here we're just doing relatively vanilla, find the map, and then make the bound tight at that map, like focus on that point. And that's worked well for these problems, but for more general sort of problems, I think it's actually an opportunity for variational methods in MCMC to overlap, because often variational methods give you exactly the kind of bound you'd like to use for this. And there's a lot of interesting ways now to find those kinds of things, and they are increasingly sort of black box. Yeah. No, we don't. We do not update the bounds while we're running. It could break detailed balance as long as you didn't correct for the way that you were. I mean, you could potentially correct for it, but here we're just doing something like fast and dirty to fit the tight bounds in the beginning because we don't need any guarantees for that, and then given the bounds, then running the chain. But you could imagine using a burn-in type period or the same kind of tricks you'd use for tuning your Markov chain and applying those to the bounds. More generally, there's also adaptive MCMC, but we haven't tried to plug these two things together. Okay, so parallel predictive prefetching is a different kind of complementary idea, and here the idea is going to be to use subsets of data to get exact Markov chains, but what we're going to be doing is using the subsets to speculatively parallelize what we're actually using our computational resources to do. And so this is work with Elaine Angelino and some other folks. So basically, the idea is to observe that the Markov chain that we actually run can be decomposed, right? A typical kind of procedure that we have for doing something like Metropolis Hastings is to make a proposal and then accept or reject that proposal, right? This is a very typical kind of process. And so we can think of this as a kind of two-part deterministic function of the pseudo-random numbers that we're pumping into this algorithm, okay? It's not surprising this is not like a novel observation, which is that these kind of Markov chains that we're simulating are consuming randomness from some space, and then they're just maps back onto that space that are consuming the randomness. And so the idea is that there's some part that is proposing a set of candidates to which you might go next, and then another thing that is selecting amongst those candidates, and that's where you actually go, right? And we can frame a lot of algorithms that we actually use in these terms. And this has the very sort of interesting property that one of those we can probably do sort of in advance. That is to say that the proposals that we make in Metropolis Hastings, right, can be sort of run out into a very large tree of all possible places we might go before we look at any data, right? That is to say that we can run our sort of pseudo random number generator anytime we want, right? We can just run it. We can just generate a whole bunch of random. A randomness from our, by calling rand on our computer or whatever. And we can, and what that does is it allows us to construct in Metropolis Hastings the tree of all possible places we might propose, right? We start at some place, and we might make a proposal to go to some new location, or we might reject that, and then we would stick, and then we would consume some more randomness based on the outcome of that, and so on. We could construct this tree anytime we want without ever looking at any data. You agree? Okay, so then all that's happening is when we see the data and we consume a little bit more randomness based on the threshold, we're deciding which path to take down the tree. Okay? So we can now think about, well, if I knew in advance somehow, some magical way, what the sort of, which path I was going to take, right? Then, and I had a computer with 32 cores, or I had a cluster with 1,000 cores, then what I could do is go off and start computing those very expensive targets in advance, right? I could just throw all them out there, I know where I'm going to be, and I go on and start computing those pies with all their zillions and zillions of terms. I could just get started now, and then I get to consume that. Then I have things running in parallel, and I get to consume the results of that when I actually get there. Now that's kind of silly, because of course if I knew what the path was, I wouldn't bother computing all this stuff. But nevertheless, I can make predictions. I can make noisy predictions. And if those predictions are pretty good, then that allows me to get some parallelism, even though it's only a single sort of sequential Markov chain. Okay? So we call this parallel predictive prefetching, because the idea is we're going to prefetch these results, like target values, and we're going to do it in parallel based on making sort of speculative predictions about where we're going to land. All right? And we can imagine different kinds of ways. I mean, a really simple thing you might imagine doing is just spamming out, right, all of the potential places you might go, right? Fill up the tree as you go. That gives you speed up, but it's going to give you logarithmic speed up, right? Because the problem gets harder and harder, bigger and bigger, exponentially fast as you go down the tree. So we'd like not to do that. Of course, we have perfect predictions. It would be essentially linear, because we'd just be looking at one at every level. And the question is, can we try to kind of find some sweet spot where we're getting kind of like better than logarithmic, but not quite, but we're not going to make perfect predictions, of course. So one thing you could do is observe that the typical sort of optimally tuned Metropolis Hastings algorithm tends to reject most of the time. Sort of rejects like 3/4 of the time. So that biases you on the tree, and that's something you can take advantage of. And this is, and some past work has done exactly that, to do very modest parallelism. But you can convince yourself, of course, that this can't give you a lot of parallelism because the bias isn't that strong. So the most speed up you can kind of expect to get in this way is something like kind of like a factor of 4. But in our world of big data, perhaps we can make much better decisions, right? So if we have a very large posterior distribution, And what we're really going to do, right, with our Metropolis-Hastings ratio is compare a very large product at one place to a very large product in another place, right? And that ratio, so what we're really looking at is the difference between two sums, that are the sums of all of the logged factors in this term. Then perhaps, even if there's 1 million factors, then maybe after we look at 1,000 factors, things will have converged enough that under, say, for example, assumptions that it's kind of approximately Gaussian, maybe we can go in and exclude entire chunks of the tree. All right? And so then what we can do is, with a very small amount of data, decide where our resources are best spent before we go off and actually compute it. Okay? So the point here is that we wind up with an exact Markov chain, okay? Because all we're doing here is deciding what to schedule. All right? So the Markov chain still computes the posterior with all million data, but the idea is to make approximation assumptions about which of those values are likely to which of those theta values are likely to actually ever need to be looked at, and abort some of those computations when clearly we're going to reject when we get to that point, or with high probability we reject when we get to that point. So the idea again is to use subsets of data to build a great scheduler for the computations we were going to do, but the answer we get, in addition to just leaving the true sort of Markov, the true posterior distribution invariant, it's actually giving you the exact same result you would get if you ran it on one computer. It's just trying to guess what things to do in advance. And so really, in some ways, this is kind of a computer science systems problem as much as it is kind of an MCMC type problem, because it requires building a big parallel thing that can make these estimates online. And it turns out that you get a nice speed up, particularly in the sort of the burn-in section of the Markov chain. And that's not too surprising, because that's a situation in which the thetas are interestingly sort of disambiguated. You make a jump and you're going to rapidly know whether it's better or worse. But then what happens is, as you run the chain forward, it becomes more and more ambiguous whether or not the data want to go to some new theta or not. And this is because kind of in high dimensions, right, your typical set all kind of looks about the same. And so as a result, you necessarily need to look at more and more of the data in order to tell the difference between two potential hypotheses. So it starts out with a very nice speed up, but then it actually degrades in practice to something that is kind of more logarithmic. So it's kind of a nice way to burn in a Markov chain in parallel in practice. And this is kind of an example highlighting this, in which along the x-axis and log scale is how many data you need to look at to make a decision about whether or not this branch of the tree is worth pursuing. And this is at two different stages of the Markov chain, of sort of running the Markov chain. You can see exactly what's going on. So in the beginning, you're able to make very rapid decisions about whether or not this branch is worth pursuing. And then later on, you're having to look at more and more of the data as you go. So as I said, this gives you the exact answer, and all we're doing here is using subsets to decide on how to parallelize it. Okay, so kind of wrapping up, I mean, the name of the game here is how do we get to use the kind of the nice algorithms like Markov chain Monte Carlo in this large scale setting, and can we do this in such a way that we get the same kind of answers we would expect to get if we did sort of cheaper and dirtier things on a single core. And I talked about a couple of different ways that in some ways are both limited, and we don't, I'm not trying to say these are kind of the solutions to all problems, but rather there's kind of attacks on how to do this when most of the work that we've been seeing in this space has only sort of given approximate Markov chains. So Firefly, again, is an auxiliary variable method that allows you to get the sort of full data posterior, but at each step you're looking at a random subset, and so you converge to the right answer. And then I talked about parallel predictive prefetching, which is an idea that allows you to use subsets of data to parallelize, to do better scheduling of the work you need to do to simulate one Markov chain. So I'll wrap up there, if there's any questions.